Today we want to talk about parameterized curves so that we can describe one-dimensional curves in R3. So we have described sets in 3 dimensions, three-dimensional sets. With a triple integral, we know we can describe a solid in R3. With a function or an equation, we know that we can describe a two-dimensional surface in R3. The third thing on the list is to describe a one-dimensional curve in R3. One thing we can imagine, we can imagine the path of a fly flying around the room. The fly isn't tracing out some surface or some solid. The fly, oh, maybe he is. I don't know. I can't read the minds of a fly. But if we just follow the path, a little line traced out by the fly as it flies through space, we can imagine the path of a fly we can imagine the path of a fly as it flies around the room. It's tracing out a one-dimensional curve in three-dimensional space. It's appropriate to think about a fly because the story goes that Descartes thought of Cartesian coordinates when he watched a fly walking around on the ceiling. Shout out to a time when thinkers had time to just kind of like watch flies as they walk around the ceiling and think about stuff. I mean, who's got time for that anymore? The fly can change direction in three-dimensional space. So the fly is flying through three-dimensional space, but if we just look at the path of the fly and imagine a curve as it moves around three-dimensional space, all we can do on that path is move forward and backward. So that's what makes the curve one-dimensional. The only options, if you lock yourself onto the path, the only options are forward along the path or backwards along the path. So that's what makes it one-dimensional. We only have forward and backward along the path. The fly can move in 3 dimensions. So it has 3 dimensions about where it can go next. But once it establishes a path, that path, the established path, is one-dimensional. All we have is forward and -1 times forward, which is backward. Since backward is just -1 times forward, it's a linear combination of forward. That still only counts as 1. And we want to be able to describe, not necessarily a fly, because a fly, it seems to move randomly. Although I bet if we watched long enough and decided we wanted to find a particular pattern, then we would just find that particular pattern because that's how the human mind works. But that's the idea. We want to be able to trace out a one-dimensional curve through three-dimensional space. Another example of a one-dimensional curve in three-dimensional space is we can imagine a roller coaster. The roller coaster exists and travels in 3 dimensions, but once you're on the roller coaster, you can either move forward or you can move backward. So also a roller coaster. That actually sounds more fun than watching a fly fly around the room, but much harder to execute. So I don't know. We have to balance that out. So we can also imagine a roller coaster as a one-dimensional curve going through three-dimensional space. Once again, the only options on the roller coaster are forward and backward, and that counts as 1. So we have seen examples of parameterized curves before. I'm going to go with everybody's favorite example of the parameterized curve, and that would be the unit circle. So our favorite example of a parameterized curve, the one that we almost always use for an example of parameterized curves, is the unit circle. This is because it's super familiar. So we know we can describe the unit circle with cosines and sines. That's like the basis for trigonometry. So we say x of t is cosine of t, y of t is sine of t, and we'll make t go from 0 to 2 pi. We'll leave an open interval on the 2 pi so we don't double up our points. So the idea here is that x and y are independent of each other and instead defined in terms of some parameter that sits outside of our coordinates. So x and y are defined independently of each other. X and y are defined independent of each other and instead written as functions of some parameter that sits outside of our coordinate system. So rather than say x is a function of y or y is a function of x, x and y are independent of each other and defined as a function of some parameter sitting outside of the coordinate system. T is not one of the coordinates. We just have x and y coordinates. You may note that in this setup, we're talking about the unit circle. So we do know that there is a relationship between x and y that we can write, but that's not how we're defining the unit circle. So we should point out that there is a relationship between x and y. This is the unit circle. But that's not how they were defined. So we do want to note that there is a relationship between x and y. I'm not saying there isn't a relationship between x and y. It's just not how we're defining the unit circle in this case. So there is a relationship between x and y because it's the unit circle, but that's not how we're defining the unit circle in this case. In particular, x and y on the unit circle are related by the equation x squared plus y squared equals 1 squared. We can also write y as two functions of x, or x as two functions of y. So we can write an equation relating the variables. We can write a few functions relating the variables. But more importantly, we're defining the unit circle with x and y independent of each other. So we can just start plugging in values of t for x and y. We can make a table of values. We just have multiple things. Rather than choosing a value of x and figuring out what y is, we choose values of t and figure out x and y. Rather than choosing values for one of the variables and figuring out the other one, we choose a value for the parameter and plug it in to find the values of x and values of y. So we can form a table of values. We're choosing values of, by choosing values of t and plugging them into x and y. This is standard operating procedure when we first learned how to graph equations. When we first learned graphing functions, we had y equals some function of x. We chose values of x. We plugged them in to find y. Here, we're just choosing values of t, plugging them in to find x and y. Here's one of the interesting things that this produces. I'm plugging in values of t from 0 up to 2 pi going around the unit circle. Here, I stopped at pi over 2 because, I mean, we know what the unit circle looks like. Since t is going to be chosen from an interval, we're picking an interval for t, there's a start and a stop. When we choose an interval for t, we get kind of a start and we get an end. What we're doing is drawing the unit circle, not just as a whole thing, but we're getting direction on the unit circle. We're establishing an orientation for the unit circle. One of the things that we get when we make a parameterized curve, since t goes from 0 to 2 pi, we establish a direction since t starts at 0 and ends at 2 pi, we establish an orientation for the unit circle. We are establishing an orientation for our curve. So when we imagine x squared plus y squared equals 1, we imagine this circle and it's just there. But now that we have values for t going around this circle, we've established a starting point and an ending point. Here's where t is equal to 0, and that corresponds to the point 1, 0. And as t goes around, we're going in this direction. We have established a direction around the circle. So up here at this point, 0, 1, this is where t is equal to pi over 2. And then down here at this point, we continue around the circle at the point negative 1, 0, t is equal to pi. So it's more than just drawing the figure of the circle. We're establishing some direction on the circle, some orientation on the circle. In particular, that orientation says start at 1, 0 when t is equal to 0, and end at 1, 0 when t is equal to 2 pi. We could describe this more, since this is like we're making a circle. We could say go around once counterclockwise. So we might, since this is just going around a circle, describe this as go once around counterclockwise, starting at 1, 0. We can see this on our calculating machines. The default way of drawing functions on your graphing calculator is just as functions, where y is a function of x. So if you want to do parameterized functions, you've got to go down to change from function to parametric. And then when you look at y equals, it has two. It's got a y, x equals, and a y equals. So if I say x is cosine of t, and then y is sine of t. Now, if we look at our window has another piece to it. It's not just the size of the window, where you see I have a range of x's and a range of y's. Not just a range of x's and a range of y's, but here I've got t going from 0 to 2 pi, and I've got some kind of step. This is how often the calculator is going to plug in values of t. It's going to start at 0, end at 2 pi, and these are the values it's going to plug in. Notice if I reduce the, if I just stop at pi over 2, it's just going to connect the dots. All we're doing here is plugging stuff in and connecting the dots. We're not actually drawing curves. It's a calculating machine. It is showing us dots. Here I only ask to calculate these 4 dots. If I increase the step size, or sorry, decrease the step size, so let's say pi divided by 4, then I'm going to get the 8 sides. I can also do like pi divided by 6 and have it every 30 degrees. And if I want to make this bigger, we do the same thing that we always do. Increase the radius. And then eventually we make it round enough. That looks like the original one. So the calculator is not drawing a circle. It's drawing a 20-sided regular n-gon, a regular 20-gon, and fooling you into thinking it's drawing a circle. Right now the calculator is thinking, these stupid humans, they think I'm drawing a circle because their mind fills in blanks. But one of the things that we want to notice is that the other thing, the reason I wanted to keep changing this up, actually, let's make it work a little bit, is that we can see the calculator drawing this with its orientation. So we could see that goes once around counterclockwise, starting at 1, 0. That was only plugging in 48. Watch it struggle. Now I'm just being mean. So the important thing is that when we make a parameterize a curve, we also give the curve some kind of orientation or direction. Any questions? Number one, why we would want to do this, we're trying to describe one-dimensional curves in R3. I know I'm using R2, that's so I can draw stuff. The reason is I want to be able to define the variables independently. I want to define my coordinates independently. Number two, we establish an orientation on the curve, and that gives us some kind of direction. Now that I've said the word direction and I've drawn things with arrows pointing, the next thing is to make this into vectors, because that's how we deal with direction. So vector forms. So now we're going to have vector style. So our unit circle, we had x of t is cosine of t, y of t is sine of t. We've got to tell our reader what values of t we want them to plug in. And we'll say this is for t between 0 and 2 pi. Now we're going to write a vector function. So here's how we would represent that with a vector. This is going to be a position vector. The first position vector will be 1, 0. And then as t goes around from 0 to 2 pi, we draw the same circle. So we're thinking of this as a position vector. So when t is equal to 0, we get that first position vector. That vector is r of 0. So if we just plug in all the values and mark the end of these position vectors, then we get our circle. And since we can see that t started down here at 0, then pi over 4, then pi over 2, we are clearly going this direction. So I just said there's an orientation going around this circle, and I just said we're going in this direction, and I just wrote a function of t that I described as a position vector. So this being a calculus class, you can probably guess what's going to happen next, because this class writes itself. This is a position vector. This is a calculus class, and I've used the word direction. So if you thought I was going to bring up velocity as the derivative of position, then of course I was, because this is calculus and that's what we do. So if we look at r prime of t, first of all, we have to know how to take the derivative of this function with respect to t. So I want the derivative with respect to t of r. We're going to write it as r prime of t. Were I a lot meaner of a person and everybody was going to be in class all the time, then I would have handed you a piece of paper with this written on it and say, find r prime of t, and not told you how it works. and make you guess at how it works. One thing you can't be afraid of if you're going into science is you can't be afraid of guessing. So if you thought, well, should I just take the derivatives of the individual components? Then you are correct. The derivative of cosine is sine. And the derivative of sine is negative cosine. And we've inherited these values of t from 0 to 2 pi, so we keep those. Take the derivatives of each of the components. Now, let's pick a point. Let's say at t equals pi. Oops, I spelled pi wrong. And we get sine of pi I minus cosine of pi j. Sine of pi is equal to let's see, 0. Cosine of pi is, let's see, 1, 0, negative 1. Derivative of sine is cosine. Derivative of cosine is negative sine. I don't know if this is a more coffee problem or a less coffee problem. I just know what solution I'm going to be applying. Derivative of cosine is negative sine. Derivative of sine is cosine. This is because I had been thinking about Calc 2. And so I've been thinking in terms of integrals. Yikes. So R prime, I'll edit that out. And then later on, conspiracy theorists can say, oh my gosh, see the smears that weren't there before? They just appeared. Clearly, he had written something in purple, then erased it, and then fixed it. I'm just kidding. I don't edit my videos. Sine of pi is still 0, so this is still 0i. But cosine of pi is negative 1. So at the point r pi, our location, our position, is going to be here. This is where we are at pi. And our velocity vector is 0, negative 1. That makes sense. That is tangent to the circle at that point. And that tangent to the circle at that point is the same way we think about direction way back in Calc 1, when we were trying to find the slope of the line tangent to a curve at a point. So here we are doing the same thing, finding the direction tangent to a curve at a point. Instead of slope, we're using a vector because we have the vector technology. So now we're just describing the direction with a vector rather than slope. So we're making the line tangent to the curve at the given point. And since we're at it, if I take a second derivative, this will be our acceleration vector. And if we look at the acceleration vector at pi, we get positive 1 I plus 0 j. And that tracks with what we know is going to be happening. So we see our velocity vector tangent to the curve. Our acceleration vector is pulling this velocity around. So it's going to have to be pointing back towards the center. The acceleration, to keep that position vector going around that circle, the velocity is tangent. The acceleration is going to have to be pointed back towards the origin to keep this velocity going around the circle. Any questions? This seems like a lot because it's kind of a lot, but it's just reframing our old stuff. We're still thinking about direction on a curve as the direction tangent to the curve. We still have that mindset of tangent to the curve is the direction of the curve. Tangent to the curve is the direction of the curve. Tangent to the curve is the direction of the curve. Tangent to the curve is the direction of the curve. So as that flies around, we want to see the position and we want to see the line, the vector tangent to the curve, tangent to the path, as the direction at that instant. When we're on a roller coaster, we want to imagine our vector, our velocity vector, tangent to the roller coaster. Not a new idea, an old idea framed with a parameterized curve. That's all. Any questions? Looking further ahead, we're describing these curves with parameterizing curves, and we're describing these positions as vectors. We're describing positions as vectors. This is calculus class. We've also spent a good deal of time talking about integrals. So we want to be thinking integration is multiplication, but one of our factors is continuously variable. And now we've just dropped vectors. And so we're going to have to think about vectors and multiplication. So it looks like we're going to be starting to do some integrals that are going to be with some vector multiplication, specifically dot product. What does dot product care about? Dot product says how much of one vector is going in the direction of the other vector. What is the other vector component? Or what is the component of one vector that is parallel to the other vector? That sounds a lot about words about direction, and that's what we're trying to track. So we're going to see some integrals with dot products, because dot products is multiplication when we have vectors. And integration is multiplication when one of our factors is continuously variable. Any questions? Comments? Snide remarks? That was a lot to drop in the last 2 minutes of a talk about parameterized curves as we head into a weekend, and you're going to quickly forget about it, which is by design. You are supposed to quickly forget about what I said about integration being going to have some dot products in it, because we'll be talking about vectors, because dot products is multiplication when you have vector factors. Integration is multiplication when one of your factors is continuously variable. You're supposed to forget that sentence that I just said over the weekend, because it's just going to sit in your subconscious the whole time. And then later I can remind you of it. And it'll seem like you're hearing it for the first time and you understand it instantly, and you'll be boosted with confidence. All right, that's going to do it for today. Everybody have a good, that's going to do it for this week. Everybody have a good weekend. I'll see y'all on Monday.